Now in this lecture we shall learn about the section 2.4 of AS 1170. So basically section 2.4 of AS 1170 part 2 2021, that basically explains us that how we can calculate the design wind pressure. So when we are talking about the clause 2.4.1, that is given on page number 19. So that basically says that when we want to calculate the design wind pressure, that is the final output. So design wind pressure, that can be, we can say, denoted as P. So that is equal to 0.5 times rho air, means density of air, and that needs to be multiplied with V design theta to the power square, and that again needs to be multiplied with CSHP, that is aerodynamic shape factor, and C dyne, that is the, we can say, dynamic response factor. So I'm writing the name also here, that first of all, if we are talking about the rho of air, that is the density of air. So density of air is basically standard value, that is 1.2 kg per meter cube. So that is a value that is used in all of the country codes. So instead of putting an additional coefficient here, we can say that design wind pressure P is equal to 0.6 time V design theta to the power square, which is then again multiplied with the aerodynamic we can say shape factor, and then again multiplied with the, we can say, dynamic response factor. So we can just write the the terminologies here again. So this is the we can say the main equation. So this is, we can say, the main equation that we shall be using a lot when we shall be dealing with our calculations. So in here when we are saying that P, the value of the units of P, that is basically design wind pressure in pascals. And we can say that the rho of air density that we have already understood, that is we can say 1.2 kg per meter cube. When we are talking about the V design theta, we are talking about the building orthogonal design wind speeds. So V design theta is equal to building orthogonal design wind speeds. So basically we can say that we shall have 4 different kind of design wind pressures if our building is having 4 sides, because we shall be having different values of V design theta from all the directions. So we can say that V design theta, according to that we can change the value of the P also. So CSHP is equal to, we can say, aerodynamic shape factor, and that we have discussed in great detail in another section of this particular course. So aerodynamic shape factor, that is basically explained in detail in section 5 and in the annexure also. So that we shall discuss in great detail. And C dyne, that is basically the dynamic response factor. So that is applicable for, we can say, tall buildings, that is applicable for, we can say, slender structures or structures which are wind sensitive. So dynamic response that is valid for wind sensitive structures. So that is, we can say, basic understanding here. So accordingly we can calculate the design wind pressure. Now when we're talking about the section 2.4.2, so section 2.4.2 basically says that or it helps us in assessment of design frictional drag force per unit area. So when we're talking about the, let us say this is the roofing on which we have to calculate the wind loads. So when wind is striking from this particular direction, we can say here that basically we are talking about theta is equal to 0 degree. But when wind is flowing across this direction here, that is along the, we can say, pitch, so in that case the roughness of this particular roofing, whether it is a plain sheet or whether it is a corrugated sheet, that do affects the, we can say, wind intensity acting onto the supporting structure. So that is basically, we can say, a drag force that is acting along the length of the roofing. So design wind frictional drag force per unit area, that is named as F. So F is equal to 0.6 time. Again, we design theta square, which is then multiplied with the CSHP. Now this CSHP is nothing but we can say a drag coefficient that can be calculated on the same principle as per the section 5 and the annexures. So that is how we can calculate the design wind pressure. So I repeat, what we have done is that with the help of VR, we have calculated VSIT beta, and with the help of the maximum values that we are getting, we have calculated the V design theta, and on the basis of that we can calculate the value of the P, that is the design wind pressure. So according to that, we can calculate all of these values. Now if we are talking about the forces on structural elements, so there are these different approaches with which we can calculate the, we can say, wind forces and wind pressure. Now as a basic physics, we all know that pressure is equal to force per unit area. Pressure is equal to force per unit area. So if we want to calculate the wind force on a particular element, what we need to do here is that whatever pressure we have calculated, that is the P, that simply needs to be multiplied with area to find out the force. And this force, we can say that unit shall be in kN per meter. P value shall be kN per meter square, and we can say that instead of this area, we can multiply one dimension to find out the UDL across the other dimension. So according to that, we can calculate either in kN per meter or either in kN. So that is the math with which we need to do. So just to give you a clear example here, so if we want to calculate the forces derived from force coefficient, calculation of forces derived from force coefficients, so that we can say is basically is equal to 0.6 times, and that needs to be multiplied with the design theta to the power square, and that again needs to be multiplied with CSHP, again needs to be multiplied with that is dynamic response factor, and in the end it is multiplied with the AZ. Now this AZ is basically, we can say is different for different members. Now if this AZ, let us say we are talking about the transmission towers. So let us say this is the transmission tower, and in transmission tower basically the members are the only one that is resisting the forces. So whatever cross-sectional area of these members, in this case, that shall be the value of AZ if we are dealing with the open structures. So this is an open structure, so whatever structural member exposed area, that shall be the value in the case of that shall be, we can say, AZ. But if we are dealing with the closed structure, let us say we are dealing with this particular building itself, this is the isometric view of the building. So whatever the cross-sectional area is there, that shall be the value of AZ if we want to calculate for a particular surface. But usually what happens is that when we are calculating these kind of values, we do consider floor by floor application. So whatever we are calculating, that we can simply considering either the force or the contributory area. So the correct term we can say is basically contributory area, that is a contribution, or we can say the area which shall resist the wind forces. That is the basic science in calculating of the wind forces and wind pressure. So as a simple math, pressure is equal to force per unit area. So if we want to find out the force, we need to multiply the wind pressure that we have calculated with area. That is we can say, basic math. Now if we want to the section that we have right now discussed is 2.5.3.3, given on page number 21. Now there is this one more important clause that is given on section 2.5.4. Section 2.5.4, page number 21. Now in this particular section, it is explained that the for rectangular enclosed building with height greater than 70 meters. So let us say this is the rectangular enclosed tall building, which maybe we can say an office building. So if the height is greater than 70 meter, and this is a rectangular enclosed building, so for that torsion needs to be applied. So why torsion needs to be applied, I shall explain it shortly, but just to give you a brief preview of the clause. So for rectangular enclosed building, this is the, we can say, rectangular enclosed building. So height has to be greater than 70 meter here, so torsion shall be applied. And based on the centricity of 0.2 times b. So centricity that needs to be applied here is 0.2 times b. Now with respect to the center of geometry of the building, so let us say this is the center of geometry of the building. So with respect to center of geometry of building, so according to that we do need to apply the torsion here. Now just to give you a brief preview here, when we're dealing with the tall buildings, the main primary term that is used when we are dealing with the tall buildings. Now tall building, as per my experience, we can say that whenever we go beyond the height of 40 meters, or we can say 50 meters also, it is compulsorily, we can say that as per my experience, it is recommended to go and check for the dynamic effect of the wind loading. Now dynamic effect of wind loading, when we are discussing about the dynamic effects, when we are discussing about the dynamic effects of wind loading, we are talking about two terms here. One term is the along wind effect. One term is the along wind effect. Second term here is the across wind effect. And both of them has to be considered together. It is not that like we have to consider only the along wind effect. It is also not like that we have to consider separately the cross wind effect. Basically what happens is that if we see any kind of building in the plan, let us say this is a 100-meter tall building and we are seeing this in plan. So let us say when the wind is flowing from this particular direction, so let us say wind flows past like this and it goes something like this. The red in trajectory is basically the path of the wind. But at the same time, what happens is that at the extreme, we can say on the negative phase, a suction kind of pressure develops. So the wind is striking at this particular phase also, but at the we can say rear side, vortex shedding phenomena, or we can say external disturbances are being created by the wind flow. So that is basically when we are dealing with the along wind effect. So as per basic engineering judgment, we can say that we only have to consider pressure on this phase only. We don't have to consider pressure on this phase. But at the same time, what happens is that there are these small disturbances or vortex shedding also happening at these particular phases. So that governs the design of the, we can say, across wind effect also. So we can say this direction is the across and this direction is along. But when we're dealing with the tall buildings, both of the directions are activated together. Both of these directions, we can say, are activated together or at the same time. So that I shall explain in a detail in a separate lecture also when we shall be dealing with the dynamic effects. But just to give you a brief preview, that is the basic concept of the, we can say, tall buildings, that along and across effect need to be considered simultaneously in one load combination. Why? Because due to the wind engineering, we can say, it is not that wind only act in one direction when we're dealing with a tall building. Due to the vortex shedding processes, or we can say external disturbances, or we can say high sensitivity to the high wind pressure zones, we can say that along and across effect needs to be considered simultaneously. Now when we are dealing with the 2.5.4, basically what happens is that although when we are dealing with the along and across wind effect, these kind of we can say torsional effect. Now what exactly is the meaning of torsion? Let me just explain you in a simple manner. We have basically these three axes. This is x-axis, this is y-axis, and this is z-axis. Now z-axis is towards you. You can say that, let us suppose z-axis is coming towards you, and let us suppose this is our building in, we can say, plan view. So this is, let us say, x-axis, this is y-axis, and this z that is coming towards you. So when we apply any forces along x, that shall lead to generation of mx, that is bending moment along x-axis. When we apply any rotational forces along y, that shall lead to development of my, that is moment along y-axis. But when we are putting a rotation of forces, we can say, across this particular direction, assuming it as a stick coming towards outside of the screen. So when we apply any rotational forces along this basically leads to the development of torsion. So that is what happens when we are dealing with the tall buildings. So when we are dealing with the, we can say, tall buildings here, so let us say this is the vertical axis. Now it is not coming towards you. Let us say this is the, we can say, vertical axis. So any rotation happening in this particular orientation, so that shall basically try to twist this particular building. So that is why it is known as the torsion, and that do happens when we're dealing with a tall building. Because one of the primary reason we can say is that wind is also a varying force. Wind is also not a same force that is acting towards the height. So it may happen that this suppose this area here, this may experience very high frequency of vortex shedding. This area here, it may not experience that much vortex shedding. So on the basis of that, this building may try to twist along its own vertical axis also. So that is why for it has been considered by the court, that is for h greater than 70 meter buildings, torsion needs to be applied. By how much eccentricity? By we can say 20% of the dimension of the building. So let us say this is the B, and this is the center point. So let us say this is the center point, and this is the B. That is the dimension of the building. So we can say that the center of this particular contribution of wind force, that is not exactly at the center, that is effect of wind force, that shall be acting at eccentricity. This is the eccentricity of 0.2 times B. So that is what this clause 2.5.4 is trying to convey to you. So I hope the concept is now clear to you. And when we are talking about the fatigue or wind sensitive structures, I shall not be discussing that here, but we shall be discussing that in the structural steel design course, because fatigue is more or less a process that is primarily being a part of the steel structure design itself. So I can say that it is explained in a very beautiful manner when we talk about the AS 4100 2020. So in that structural steel design course, we shall be discussing about the fatigue analysis also. The simple concept of fatigue analysis is that as a individual also, we can say, let us say you have to let us say this is the running ground, and you have to consider make complete one round of this particular ground. So let us say you ran for approximately 400 meters. So let us say you have to make 100 rounds of this particular ground. So we cannot say that you shall be running with the same intensity at the first round also, and at the, let us say, 70 or 80th round also you shall be having the fatigue. So same is the case for, we can say, structural steel also. So what we usually do is that, let us suppose we are targeting a fresh material strength is 200 Newton per mm square. But if we know that the structural steel section is in fatigue, and it has to perform a very high number of stress cycles, So we can say that for a particular number of stress cycle, equation is there. Instead of 200, we can target only 160 Newton per mm square as the strength. So steel is designed only for that, because we know that due to the very high number of stress cycles, it shall have a fatigue behavior and it shall lose its strength. So that is the concept of the fatigue analysis. After that, 2.5.8. Now 2.5.8 is the, we can say, a best part of AS 1170, and that is either, I think, covered. The parallel explanation is only given in ASCE 07 code only. That is basically the American code, which deals with the, we can say, wind load, all type of loading calculations. Now, if we are dealing with the section 2.5.8 of AS 1170, it is talking about the wind-borne debris, the one that we had discussed in the earlier lecture also. So when we are talking about the wind-borne debris, it is basically the clause 2.5.8. That basically deals with the impact resistant testing. We have already understood, we have already discussed that why it is very important to ensure that the glazing or the outer glass or the outer facade, it does not fail at the time of the cyclone. Although as a complete, glass window, that may have the strength. But what if a stone or a small log of wood comes and simply, breaks this window or breaks this glass? So to attend that, this AS 1170 is giving us guidelines of do the impact resistant testing. So what shall be the debris impact loading? Debris impact loading. So that can be taken from, we can say, page number 23 of AS 1170. So what it says that there are basically two, we can say, parts. The part A deals with the timber test member. So part A deals with the timber test member. What is the size of that timber test member? It has basically a mass of 4 kg and density of at least 600 kg per meter cube, and that is achieved in the timber, so that is not an issue. And nominal cross-sectional area of 100 mm by 50 mm. And how it has to be impacted. So we are broadly dealing with wall surfaces and roof surfaces. So if we are talking about the wall surface, so for wall surface, it has to impact at 0.4 times VR. That is the regional wind speed. And if we are talking about the roof surface, so for roof surface, the pitch is important. So if the pitch for, let me just write the roof surface here. So for roof surface, if the pitch is greater than 15 degree, at that point we have to impact, or we can say, because all this is done in the test laboratory. So there is this testing lab in which we do all these kind of tests. So in for roof surface, for greater than pitch 15 degree, it has to act as 0.4 times VR into sine of roof slope. So that is the speed at which we do need to hit this particular wall surface in the test laboratory. And if it is less than or equal to 15 degree, for that we have to impact at 0.1 time VR. So that is the basic testing procedure that is given. And after that, if the second testing that also needs to be done is with the spherical steel ball. So for spherical steel ball, we can say that the diameter has to be 8 mm and gram weight has to be 2 gram mass, and that has to be impacted at 0.4 times VR normal to wall surface. So let us say if we are making a glass window on the wall surface, the glass window has to be strong enough such that all of these the timber mass and spherical steel mass, when it is impacted in the test laboratory, it shall remain intact. And similarly for when we're talking about the roof surface, So for roof surface, again it is dependent on the pitch. So for it can be 0.4 times VR for pitch greater than 35 degree, and 0.3 times VR for, we can say, normal to roof surface for less than or equal to 35 degree. So let us say this is the roof surface here. So this is normal to roof surface. So we shall take a 2 gram mass of 8 mm steel spherical ball, and we shall impact it at 0.4 times 0.4 times VR if the roof pitch is greater than 35 degree, and 0.3 times VR if the roof pitch is less than or equal to 35 degree. So that is basically the we can say impact loading from windborne debris testing that needs to be done. Now all these, it is not like that we are dealing with the random numbers here. A lot of research has been done for, we can say, these impact test debris. It is not that like we have to apply the spherical steel ball and timber mass at the same time. It has to be applied at the different time intervals. So it is not like that, we have to deal with both the or conservative approach. We can say that spherical steel mass testing and timber mass testing has to be applied at the different time spans.